Hi everyone, this video will follow up on our class from earlier this week by explaining how to do the one-way chi-square test in SPSS. First, let's quickly review what the one-way chi-square test is and how it compares to the other test that we learned a few weeks ago. As you'll recall, the one-sample t-test is used in situations where we're working with one continuous variable. We make a prediction about what the mean is going to be. That prediction we call mu. And we then compare the mean of our sample against the value of mu to see whether the mean of our sample is or is not significantly different from what we expected it to be, namely mu. A one-way chi-square test, as we talked about in Monday's class, follows a very similar process but works with a categorical variable instead. In other words, what we're doing here is we're making a prediction about what percentage of people we expect to fall in each of the categories that makes up that categorical variable. Then we collect data from our sample and we compare the percentages that we actually found against the percentages that we expected to find to see whether they are different from what we expected to find. Today's video will work through three examples of how to perform one-sample t-tests one-way chi-square tests in SPSS, some of which will be one-way chi-square tests of equal preferred proportions, where we're expecting all of the groups to be equally large. Others will be tests of known proportions, where we are expecting the groups to not necessarily all be the same size. The first two examples will be based off of the class survey data that you all provided back at the beginning of the semester. One of the questions on that class survey asked you to report what your favorite ice cream flavor was, with three options: vanilla, chocolate, and strawberry. If you'd like to follow along, by the way, you can see at the top left of the screen we are using the data file called 212 survey spring21.sav, which is available on our website. Let's say I wanted to know whether in our class vanilla, chocolate, and strawberry are equally popular flavors. In other words, are the numbers of people who selected vanilla, chocolate, and strawberry equal to each other, or 33% of each of the class selected these options? Our null hypothesis would be that there is no difference in the frequency of people picking vanilla, chocolate, and strawberry as their favorite ice cream flavor. In other words, our null hypothesis would predict that 33% of people prefer vanilla, 33% of people prefer chocolate, and 33% of people prefer strawberry as their favorite ice cream flavor. The alternative hypothesis says that the three ice cream flavors are not equally popular. In other words, it predicts that the observed percentages will not be 33, 33, and 33, but rather some will be higher than that and some will be lower, depending on which flavors are more popular and therefore chosen by more people. In the data file 212 survey s21.sav, we see that ice cream is a categorical variable with three categories: vanilla, chocolate, and strawberry. To run the one-way chi-square test, this test is actually a little harder to find than most of the other tests that we're going to be working with in here. We're still going to go into the Analyze menu, but we are then going to go all the way down to the option called Non-Parametric Tests. That opens up another box where the bottom option says Legacy Dialogues. And when you hover over the words Legacy Dialogues, you will see an option for the chi-square test. So this is where the one-way chi-square test is hidden in SPSS. When you click on the chi-square test, this is the window that will pop up. As usual, we have a list of all of our variables on the left-hand side. The first thing we're going to do, as we always do, is we're going to find the variable that we're interested in testing, which in this case was the question that asked you to report your favorite ice cream flavor. We're going to click on that variable and use the arrow box in between the two boxes to move it to the test variable list. Now, at this point, we have to tell SPSS what our expected values or expected percentages are. For a test of equal proportions, this is very easy, because by default, under expected values, the option for all categories equal will be selected. So if we want to run a chi-square test of equal proportions, we don't have to do anything else other than move the variable over. The reason for that is because the option for all categories equal is already been chosen. So if we just leave that selected, SPSS will know that our null hypothesis says that these three categories are not different from each other in terms of the number of people who selected vanilla, chocolate, and strawberry. As we'll see later in this video, we only need to input the values manually if we're running a test of known proportions rather than a test of equal proportions. But by leaving this box checked, what SPSS will do is it will look at this ice cream variable, it will see that it has three categories, and from that it will infer that we are expecting 33% of the people to be in each of these three ice cream groups. When we click OK, this is the output that we should see. The table on the left gives us our observed and expected values, which we talked about in class as the basis for the chi-square formula. The table on the right, which we'll talk about in a minute, gives us the actual results of the chi-square test. In the table on the left, the first place we're going to look is at the expected n's. What this is the number of people who we would expect to fall into each category if the null hypothesis is true. So in other words, if it really is the case that vanilla, chocolate, and strawberry ice cream are equally popular, we would expect, out of the 75 total people in our sample, that 25 of them would have chosen vanilla as their favorite flavor, 25 would choose chocolate, and 25 would choose strawberry. Very similar to the example that we talked about in class. The observed n column tells us the actual results of our study. How many people actually chose each of these three flavors as their favorite? As you can see, in this class, 30 people chose vanilla as their favorite, 30 people chose chocolate, and only 15 people chose strawberry. So compared to what we expected, we had more people choosing vanilla and chocolate and fewer people choosing strawberry. However, we don't yet know, until we look at the results of the chi-square test, whether or not this is a significant difference. Are the observed numbers different from what we expected? The top part of the test statistics table gives us our chi-square statistic and the degrees of freedom. The chi-square statistic here would be exactly 6, so we would write it as 6.00. And there are 2 degrees of freedom because we have 3 ice cream flavors, so 3 categories minus 1 leaves us with 2 degrees of freedom. Our p-value here shows up as 0.050. Now this is obviously a very weird situation because usually we look at this number and we ask ourselves, is this number greater than or less than 0.05? In this very unusual case, it's equal to 0.05. This rarely happens, but in this case, what we're going to do is we're going to double click on that p-value to get more decimal places. So when we double click on 0.050, what we see is that p actually is equal to 0.0498. So we do have a p-value here that is barely, just by a hair, less than 0.05. Therefore, we are going to reject the null hypothesis. In other words, our null hypothesis said that vanilla, chocolate, and strawberry were all equally popular ice cream flavors. However, we are going to reject that. And our conclusion is going to be that in our class, they are not all equally popular ice cream flavors. Strawberry is less popular than vanilla and chocolate. So here's how we would write up our answer in a complete, grammatically correct, and APA formatted sentence. Start by naming the test that we did. A one-way chi-square test showed that people in our class were not equally likely to choose vanilla, chocolate, and strawberry ice cream as their favorite. As you can see from those percentages in blue, vanilla and chocolate were more popular, whereas strawberry was less popular compared to what we expected, which was 33% in each of the three categories. At the end of our sentence, we give the results of our chi-square test. So we include the chi-square symbol, which as a reminder you can get in Microsoft Word by going to Insert Symbol. You'll find the whole Greek alphabet in there. With 2 degrees of freedom equals 6.00. Remember, we have to always include 2 decimal places, even if those decimal places are zeros. And then here's one key difference between doing a problem like this by hand versus doing it in SPSS. When we do a problem by hand, we end our sentence in one of 2 ways. If we rejected the null hypothesis, we say p is less than 0.05. If we retained the null hypothesis, we write that p is greater than 0.05. When doing a problem in SPSS, however, because SPSS gives us the exact value of p, we are going to write the exact value of p in our answer. So in this case, we're going to write the number that SPSS gave us, which is 0.050. Another thing to notice about this, all numbers get rounded to 2 decimal places, as we've talked about all semester. Means, standard deviations, chi-square statistics, t-statistics, and so on. The only exception to that rule is the p-value. Because p is such a special number, it gets a 3rd decimal place. So we are always going to report the p-value to 3 decimal places rather than 2. If we want, we can also be a little more specific by adding a second sentence to our answer. So we could specify that we expected 33% of people to fall in each of these 3 categories, vanilla, chocolate, and strawberry. But compared to what we expected, we found that vanilla and chocolate were more popular and strawberry was less popular. Let's now try another example that shows how to do a one-way chi-square test of known proportions in SPSS. What I have on this slide are data from tens of thousands of college students who played the game Never Have I Ever and answered whether or not they have ever done the things listed on the slides. As you can see, some of these questions correspond to things that I asked you in our class survey at the beginning of the semester. So if we treat these data as coming from the population and representing all college students everywhere, what we can do is we can see how our class compares against these college students in general. Let's look specifically at the question, have you ever had braces? In the general population of college students, 54% of college students have had braces, 46% of college students have not ever had braces. And of course, those 2 percentages add up to 100%. What we're going to do in this example, using the data from the class survey that you filled out at the beginning of the semester, is first figure out what percentage of people in our class has had braces in their lifetime. Then we will compare that number against 54% to see, compared to the general population of college students, are the people in our class more likely, less likely, or equally likely to have ever had braces in their life? So we'll have to remember these numbers for the future slides. In the general population, 54% of college students have had braces, 46% have not. So our null hypothesis is going to say that students in this class are no different from the general population. In other words, our null hypothesis will say that the percentage of people in our class, whatever it turns out to be, who have had braces is not different from 54%. The alternative hypothesis says the opposite of that, namely that the percentage of people in our class who have had braces is different from 54%. We're going to be using the same data file because we're still using the class survey data, and as a reminder, here's where we're going to find the one-way chi-square test hidden in SPSS. Analyze, non-parametric tests, legacy dialogues, chi-square. As we saw a few slides ago, when we click chi-square, this is the window that pops up we again are going to identify the variable that we're interested in. Have you ever had braces? And we're going to move that variable into the test variable list. Now, if we were to click OK right now, we would have a problem. Because by default, SPSS assumes that we're doing a test of equal proportions. So if we were to click OK right now, SPSS would test whether the percentage of people who have had braces in our class is different from 50%. In other words, SPSS would assume that because we have two categories, people who have had braces and people who haven't, it would assume that we're running a test of equal proportions, and therefore we're expecting there to be 50% of people in each category. However, that's not what we're doing. As we saw on the previous slide, we are expecting 54% of people to have had braces and 46% of people to have not had braces. So what we're going to do is in this expected values box, we need to manually tell SPSS what our expected values are. What are the known proportions that we want to compare our sample against? They are not going to be all equal. We need to tell SPSS that we are expecting, if the null hypothesis is true, that 54% of our class has had braces and the other 46% hasn't had braces. So we're going to have to put those numbers into SPSS, 54 and 46%. Here's the tricky part. We have to enter those two numbers, but the order in which we enter those numbers is important. We have to enter them in a specific order. To figure out what the correct order to enter those numbers is, we need to go back to variable view. That's the tab at the bottom left-hand side of SPSS that shows us a list of all of the variables that we have in our file. We're going to find the braces variable, which is toward the bottom, and we're going to see how that variable is coded by clicking on the values box. When we click on that values box, we should see a pop-up window that looks like the one on the right, which tells us that for this particular categorical variable, anyone who has had braces is given a 1, and anyone who hasn't had braces is given a 2. This tells us the order in which we have to enter those expected values. We have to enter them in the same order. In other words, since yes is 1 and no is 2, we're going to have to enter the expected value for yes first and the expected value for no second. So since we expect 54% of people to have answered yes and 46% of people to have answered no, we are first going to type in 54 into the box next to where it says values, and we're going to click the add button right beneath that. We are then going to type in that same box 46 and click the add button beneath it. When we're done, we should end up with a window that looks like this, where we not only have entered our expected values, but we've entered them in the correct order. We expect 54% of people to answer yes and 46% of people to answer no, I've never had braces, based on the results of that population survey. It is only once we have entered all of these expected values and entered them in the correct order that we should click OK to see the results of our analysis. Here are our results. And as we saw before, the table on the left gives us the observed and expected values for each category. The table on the right gives us the results of the chi-square test itself. First, we are again going to look at our expected values for each category. Because there are 75 people in our class, if exactly 54% of our class has had braces before, that would mean that 40.5 people out of those 75 people would have answered yes to that question. In other words, 40.5 is exactly 54% of 75. The other 34.5 people would not have had braces, according to the null hypothesis. In other words, these are the numbers that we would expect to find if the people in our class are no different from the general population in terms of whether they had braces or not. What we actually found is that of the 75 people in our class, 41 of you have had braces, 34 of you have not. And as you can probably see, the observed values and the expected values are very close to each other, suggesting that the people in our class are not different from the general population. However, we don't technically know that until we look at the results of the chi-square test. As we saw before, the top part of this table gives us our chi-square statistic, which in this case is 0.01, so a very small number. And it gives us our degrees of freedom. We only have two categories here. You either had braces or you didn't. So 2 categories minus 1 leaves us with 1 degree of freedom. Most importantly, we have our p-value, which is very large as far as p-values go. Our p-value here is 0.908, which is much, much larger than 0.05, telling us that we do not have strong evidence of a difference between our class versus the general population. Therefore, we are going to retain the null hypothesis, and our conclusion is going to be that the percentage of people in our class that has had braces was not significantly different from that same percentage in the general population of college students. Is not different from, and that should say 5.8%, sorry about that, who don't know how to ride a bike is not different from 5.8%. That is going to be our null hypothesis here. So following the steps that we just went through in SPSS, including entering the appropriate expected values and entering them in the correct order, what you can do for Monday is practice running this test to see how the percentage of people in our class who don't know how to ride a bike compares to the national average of 5.3%. For our last example today, we're going to draw upon a famous psychology study that I'm guessing most, if not all of you, are familiar with. If you've taken a social psychology class, you've certainly talked about the Milgram obedience study. But even if you've taken intro psych, which I'm sure you all have, you're probably familiar with the Milgram obedience study to some degree. For those who may not be familiar, the way it works was as follows. 2 people come into a laboratory under the impression that they are participating in a study about how punishment affects people's learning. However, only one of those people is actually a participant. The other person is what's called a confederate, or in other words, an actor who's pretending to be a participant but is actually part of the study and in cahoots with the researcher. Long story short, those 2 people are assigned to one of 2 roles. The participant is assigned to play the role of the teacher, and the confederate, who again the teacher doesn't realize is a confederate, is assigned to play the role of a learner. The learner is taken to an adjacent room and given a list of words to memorize, while the teacher sits in the next room next to a shock generator. The teacher is led to believe that every time the learner makes a mistake on this memory test, they are supposed to administer an electric shock to them, and that the goal of the study is to see whether people learn faster when they receive more and more severe electric shocks. So Milgram has created a situation where the teacher, who is the participant in the study, believes that they are inflicting harm on another person. Now, the real goal of the study, unbeknownst to the teacher, is to see whether the teacher will continue to inflict these painful shocks on the learner simply because the experimenter is telling them to. And it's important to note that even though the teacher didn't know that the shocks weren't real, they were not in fact shocking the learner. The learner was screaming and pretending as if they were in pain, but in fact there was no shocks being delivered. So again, the goal of the study was to see, will the teacher inflict harm upon another person simply because the experimenter is telling them to? If you've never seen original footage of this study and you have a few minutes and you're curious, I would highly recommend it. Unfortunately, the link at the bottom of the slide no longer works, but if you Google Milgram obedience study video, you will certainly be able to find somewhere online original footage of this study, and you can actually see how uncomfortable the participants were with the idea that they were inflicting harm on another person simply because a man in a lab coat was telling them to. Even so, the majority of participants in this study were willing to inflict what they thought were very painful electric shocks on another person simply because the experimenter was telling them to do this. Now, as you can probably tell from the fashion and the haircuts and the quality of these photos, these studies were originally done a long time ago, back in the 1950s and early 1960s. It is reasonable to ask whether, if we were to do these studies again today, would people be equally willing to obey the experimenter? Now, for ethical reasons, it wasn't until about 10 years ago that this study was replicated, that researchers were able to do this study again and see whether people were just as willing to obey the experimenter today as they were back in Milgram's time. To be exact, in one of Milgram's studies, 82.5% of participants did obey the experimenter, meaning they administered an escalating series of electric shocks to the person who was the Confederate in the study, simply because the experimenter told them to. That was back in 1963. Now, if we were to do this study again in 2009, might the percentage of people who obey change? I think if you think about cultural differences between 2009 and 1963, you could maybe make an argument for why people might be more obedient today than they were back then, or maybe less obedient today than they were back then. A researcher named Jerry Berger wanted to answer this question. So what he did back in 2009 is he recreated the Milgram study to see if people in 2009 are more, less, or equally likely to obey compared to people in 1963. In the data file berger.sav, we have data from Berger's study. What we can do is we can use a one-way chi-square test to see if the percentage of people who obeyed in Berger's 2009 study is or is not different from 82.5%, which is the percentage of people who obeyed in the original 1963 Milgram study. For each person, we know only one thing. Did they obey, yes or no? So we have a single variable called obedience. For each person, they either have a yes or they have a no for that variable. If we run the chi-square test, we are of course going to select the variable that we're interested in and move it into the test variable list. Now, this is not a test of equal proportions. We are expecting, under the null hypothesis, that 82.5% of people will obey and that 17.5% of people will not. In other words, the null hypothesis says that the results of the study in 2009 are going to be no different than the results were in 1963. So since we're doing a test of known proportions, we have to tell SPSS the expected percentages for both categories, people who did obey and people who didn't. Remember from a few minutes ago that the order in which we enter these expected values is important. It has to correspond to how the variable is coded. So if we want to make sure that we're entering these expected values in the correct order, we should go to Variable View, click where it says Values, and see how that variable is coded. In this case, anyone who didn't obey the experimenter was given a 0, and anyone who did obey the experimenter was given a 1. Since 0 is a smaller number than 1, we're going to have to enter the expected value for no before we enter the expected value for yes. In other words, we have to make sure that the order corresponds. Based on the results of the original Milgram study, if the null hypothesis is true, we're expecting that 17.5% of people will not obey, meaning they will have zeros or no's for this variable, while the other 82.5% of people will obey, meaning they will have ones or yeses for this variable. So we're going to make sure to enter 17.5 first and 82.5 second when inputting our expected values before we click OK to run the test. Here is the output from the test. Now, as we saw before, the left-hand table tells us the observed and expected values for each category. The right-hand table gives us the actual results of the chi-square test. In our sample, which consisted of 40 total people, 30 people did obey the experimenter, but 10 people did not. If the null hypothesis were true, we would find that 33 people, in other words, 82.5% of our sample, did obey the experimenter, while the other 7 people did not. So compared to what we expected, we had slightly fewer people who obeyed the experimenter and slightly more people who didn't obey the experimenter. But remember, we don't know if this is a significant difference until we look at the results of the chi-square test. If we look at the table on the right, we see that our chi-square statistic is fairly small, 1.56, with 1 degree of freedom. And more importantly, our p-value of 0.212 tells us that we did not find a significant difference here. Because that value is greater than 0.05, we are going to retain the null hypothesis, and our conclusion is going to be that the results of the 2009 study were not significantly different than the results of the original 1960s Milgram study. In other words, people in 2009 were equally likely to obey, not more likely, not less likely, but equally likely to obey when compared to people from 60 years ago. If we wanted to write up our results, here's how it would look. A one-way chi-square test found that the percentage of people who obeyed the experimenter in 2009 was not significantly different from the percentage who obeyed the experimenter in Milgram's original study. In the 2009 study, 75% of people obeyed the experimenter. In the original study, 82.5% of people obeyed the experimenter. And the results of our chi-square test, specifically the p-value, tell us that that was not a significant difference. There is a picture of Jerry Berger and a screenshot of the title of his 2009 paper, Replicating Milgram, Would People Still Obey Today? Here's how Berger wrote up his results. Now, our data did not exactly recreate his data, but our findings are similar. Notice how the way he wrote up his results in this published scientific paper is very similar to what we've been doing in class all along, right? He found that there was no statistically significant difference between the percentage of people who obeyed in 2009 as compared to 82.5%, which was the percentage of people who obeyed back in the 1960s. Notice he also follows APA format. He's got his chi-square symbol, he provides the value of the chi-square statistic, and he provides the p-value.